So today we're going to be looking at the p-value method for hypothesis testing. So I'm starting with this flow chart. We looked at it last lesson. We didn't really talk about it because we could talk about it today. So for the p-value, we have to start by identifying what kind of tail we're looking at. Either a left tail, right tail, or two-tail test. And remember, we determine our tails based on our alternative hypothesis. So if we have a left tail test, the p-value is the area to the left of the test statistic. The first step is find the test statistic. Second step, either use your chart or your calculator and find the area to the left of the test statistic. If it's a right tail, it's the area to the right of the test statistic. So where it gets a little tricky is with the two-tail. So if it's when it's a two-tail, you have to look, is the test statistic to the left or the right of the center? If it's to the left of the center, you find the area to the left of the test statistic, and then you have to double it. If it's to the right of the center, you find the area to the right of the test statistic and double it. Just like we cut the alpha in half for a two-tail, we have to double the p-value from that area in order to get the actual result. Okay, so what does the p-value tell us? Well, if we're looking at the p-value, we compare it to alpha. If p is less than alpha, we reject the null. So this takes the place of having to look at our critical values and determine where our test statistic is at. Let's see why that is. If we have a test statistic, let's say it's a left tail. So here is our critical value. Then the critical region would be over here. Well, that critical region is alpha, right? That's alpha gets us our critical value. So this area over here is based entirely on alpha. Well, that's why we compare p to alpha. Instead of looking at the actual values, the critical value and let's say the test statistic is over here, then instead of comparing, oh, is the test statistic to the left or the right of the critical value, is it in this shaded region or not? We instead look at the area to the left of our test statistic. So we're looking at all this area, and we're like, okay, so is this area bigger than alpha? Remember, alpha gives us that area there, so that's how we can compare them directly. Instead of just looking at the critical values and the test statistic, we can look at the test statistic's area and the alpha value. So let's look at an example. We did this one before, last lesson, but we used the traditional method. So we have all the info already done for us, critical values, we even came up with a conclusion. But this time we're going to look at the p-value. We're going to determine the p-value based on this situation. So the first thing I want to do is look at what kind of tail I'm dealing with. Okay, not equal to. Remember, look at the alternative. Not equal to two-tail. So we got a two-tail going on. So we found our test statistic was 0.67. Well, 0.67, that's the right of our mean, right in the middle. So we're going to have to do the area to the right of this 0.67 and double it. So if you use the chart, look up 0.67, 0.67. So that's right here. That gives us 0.7486. I'm going to write that down. So 0.7486. So let's recall what that actually is. That's the area to the left of 0.67. Or we use the area to the right of 0.67. So I'm going to do 1 minus that answer. That's going to be 2514. And then what do I have to do next? Well, if I look back at that flow chart to the right, so we get the area to the right, and then it's twice that area. So we have to double it since it was a two-tail. That's going to give me 0.5028. and that would be my p-value. So we know that if p is less than alpha, we reject the null. Well, if we look, 0.5 is definitely not less than 0.05. So we fail to reject the null. And since our claim was in the null, again, there's not enough evidence to reject the claim that the proportion of p's with yellow pods is equal to 1/4. So that goes back to this chart right here. Again, you need to know this chart. Determine where the claim is, then determine if we reject the null or fail to reject the null. Our claim was in the null, and we failed to reject the null. There's not enough evidence to reject the claim that, whatever it may be. So that's how we get the p-value from the chart. Now, we already know how to do that on the TI, because we did it before. Let's compare the results. Since I was using the chart, I expected it to be a little different, because the TI had actually used this entire value in here, whereas we just used 0.67. So our, yeah, I think I already typed this in. Yep. So I got all the information in here already, so we could just go ahead and hit enter. 0.5021. Very close to 0.5028. Again, whether or not you use the calculator or the chart, it's up to you. Either way, you should not have a significant difference to compare to alpha. If we look, alpha's got 2 decimal places, and these are the same to 2 decimal places. They're the same to 3 decimal places, pretty much. Okay, if we look at the Casio, what did we do on the chart? I'm my way here, hang on. What did we do on the chart? We looked up the area to the right of 0.67. Well, think back a few chapters. How do we find the area underneath the curve? That's the same as the probability. That's the normal CDF. So go to Mode, Distributions, Normal CDF. The lower bound, well, let's use the 0.67 first, and then I'll use this exact value. We'll compare them to this number and then to the TI. So I use 0.67 for my lower bound. My upper bound, and it was pointed out last time, I forgot to hit the times 10 to the button on one of the problems last time. And these problems, since we've got a standard normal, it's really not going to make a difference. This is just getting a really big number. And for standard normal distribution, 99 is a really big number. But just to be safe, go ahead and do 1 times 10 to the 99. Again, we don't want to change these. We're looking for the area underneath the standard normal distribution curve. So we get 0.25, blah, 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 blah. Sure, why not? So what I'm going to do is I'm going to go back to mode 1, take my answer, and double it. Because, again, it was a two-tailed test. 0.5029 if we rounded it. So still a little bit different than this one because, again, we have some rounding issues with that chart. This guy's not rounded. But if we compare it to the TI, it's also not exactly the same. Well, how could we get it the same? Leave our test statistic, oops, there it is, as a variable. Let's see. Clear that. I got a fraction inside of a fraction, 152 over 580, minus a fourth, over a square root of a fraction, 1/4 times 3/4 over 580. Now this is my test statistic, the 0.6712, et cetera, et cetera, et cetera. We rounded it to 0.67 for the chart, and at first, whenever we did it in the Casio, the TI doesn't round it. So let's take this value and store it to A. If you remember the process, it's shift this button right here above 7, and whichever letter you want to store it to. I like to store it to A because why not? So now if I clear that out, A should be that number. Now I'm going to go to Mode, Distributions, Null CDF, lower bound of A. So we saved it in there, so we can type it right there. Again, put infinity in there as best we can. Now let's compare that p-value to the calculators. It's different. Why? We didn't double it yet. So go back to mode 1, answer times 2 to double it. 0.50206, 0.50206, and then 2, that's the same. It still gets a little bit different. So the engines in both of these calculators are slightly different, so they're going to get slightly different answers. But all three methods will get you a good enough p-value. So we're going to go 4 decimal places on our p-values, and whatever it is, it is. If you use the chart, the Casio, the TI, it'll be fine. So today we're just going to do a bunch of examples of hypothesis testing using the p-value method. And don't forget this. You need to know this so we can state our conclusions. All right. So again, we're just going to do the p-value today. Last video was on the traditional method. This video is going to be just the p-value. Your quiz will be on both. In a survey of 703 randomly selected workers, 15.93% got their jobs through newspaper ads. Consider a hypothesis test that uses 0.05 significance level to test the claim that less than 20% of workers get their jobs through newspaper ads. So again, write down what we know. N is 703. P hat is 15.93%. Change that to a decimal. And remember, TI users, you're going to have to multiply this P hat times N to get your X value. And round it because we can only have full numbers for the binomial distribution. Consider a hypothesis test that uses the 0.05, so off is 0.05, to test the claim that, okay, let's write down our hypotheses, our null, and our alternative. And again, for the alternative, you can use H1 or HA. I'll be using H1. For the null, I always use H null. I don't think there's anything else you would use. So test the claim that less than 20% of workers get their jobs through blah, 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 blah. So what we're going to do is, P is what we're dealing with. It's less than 20%. Less than 20%. There's my claim. It's in the alternative. Remember, the alternative does not have equality in it. So if your claim is a less than, or a greater than, or a not equal to, that's in the alternative. The null would be, in this case, greater than or equal to, but it's got to have equality in it. It could be equal to, less than or equal to, or greater than or equal to. It's always the opposite of the alternative. So if if the alternative is less than, the null is greater than or equal to. We've got P now is 0.2. That makes Q 0.8. Remember, those are complements. All right, now we have enough info. We're going to calculate our test statistic like it tells us to. If you don't remember, look on your formula sheet, second page, top left. There it is, test statistic. So the proportion is right there. That's what we need to use here. To calculate our test statistic. p hat minus p over the square root of p times q over the square root of n. Sorry, over n. We already have the square root. Thinking mean for a second. So this is our test statistic. Let me change the color. This is the test statistic we're dealing with. Type it in your calculator and get your answer. Again, if you're using a TI, just type in your information. It gives you everything you need. It gives you the test statistic and your p-value. Casio users, just go to mode 1 and type it in. So we get negative 2.697, blah, 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 blah. So to be safe, I'm going to go to 4 decimal places. And again, we only care really about the 2 decimal places, because that's what we're going to look up on the chart, 6978. Negative 2.697, there we go. So what we're going to look up on the chart is negative 2.70. And let's see, it's a left tail. Thank you, Alternative, for telling us that. So we have a left tail test. That means we're going to look at the area to the left of the test statistic, which is just given to us directly from the chart. So if we look up negative 2.70 right here, that's going to be 0.0035, and that's our p-value. It's a one-tail test. We don't double it. It's a left-tail test. We look at the area to the left. What does the chart give us? Area to the left. Let's look at the TI for a minute. Compare that result to the TI. So T was 0.2. X, whatever 703 times 0.1593 gives us, so we're going to have to round it to 112. 703 for N. And it's a left tail. This matters for our p-value. It didn't matter for the test statistic, but it does matter for what our p will be. And if we calculate 0.00350, etc. So really close to what we got from the chart. Now you could also do this, you could also use the inverse norm on the TI, but why bother? Because it gives you your test statistic without doing all the work, and it also gives you your p-value without doing the work. So TI users, you got a huge advantage here. Shouldn't be failing. Casio users, still really not that bad. If we go to mode, distributions, normal CDF, we need the area to the left of our test statistic. So we're going to just do negative infinity for our lower bound. Upper bound, I'm going to go ahead and just use 2 decimal places. So we get, this is a decimal with 2 zeros, then a 3 and a 5. Same thing. Decimal, 2 zeros, a 3 and a 5. I rounded that 4 to a 5. Same thing whichever way you do it. Okay. So that's how we do a p-value. Now, let's get our conclusion. Alpha's over here, P's over there. 0.003 is definitely less than 0.05, so P is less than alpha, we reject the null. All right, P less than, I need an alpha symbol. P is less than alpha, so we reject the null. Now we can write our conclusion, our final conclusion. P is less than alpha, reject the null, there, and the alternative was our claim. So there is enough evidence to support the claim that less than 20% of workers get their jobs through newspaper ads. Okay. So again, this chart tells us how to write our conclusion. If you don't know it, you're screwed. Know this chart. So there's our conclusion based on a p-value test. Now, most times you can use either p-value or traditional method. I will design the quiz where you either have to give me the p-value or you have to show me the critical values and the proper curve sketch. Makes you know both ways. Let's do another p-value test. Okay. In one study of smokers who tried to quit smoking with nicotine therapy, 39 were smoking after 1 year of treatment, 32 were not smoking after 1 year of treatment. Use a 10% significance level test to claim that among smokers who try to quit with blah, 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 the majority of smokers are smoking after a year of treatment. Okay, so I'm going to start with my hypothesis test. H0 and H1. Majority are smoking after a year. Majority would be greater than 50%. So P is greater than 0.5. So whenever we say majority, that means more than 50%. That's our claim. That makes our null less than or equal to 0.5. Okay. N. What's N? Where'd I get that from? 39 were smoking, 32 were not smoking. 39 plus 32 gives us 71 smokers. So P hat is going to be, well, what are we testing? That majority are smoking. So we want the smokers. 39 were smoking. Okay. So now we need alpha value of 0.1. P is 0.5, so Q is 0.5. And now we need to get our test statistic. You can look up the formula. P hat minus P over the square root P times Q over N. So again, I'm going to do this on the Casio because TI users will probably just type it in and be done with it. Oops, few too many there. 39 over 71 minus 0.5 over the square root of 0.25. 0.5 times 0.5, 0.25, 71. So we get 0.8307. And again, I like to round my test statistic to 4 decimal places in case we're using the critical value method, the traditional method. Sometimes they have 3 decimal places, so 4 will always get us what we need. For the p-value method, we're just going to go with 2 decimal places. So now, let's grab the p-value. First, what's our tail? Right tail. So what am I going to do? I'm going to look at the area to the right of 0.83. 0.83 right here. I write that down, 0.7967. 0.7967. 1 minus, because that, the chart gives the area to the left, 1 minus gives the area to the right. It's going to be 0.2033. It's a one tail, so there we are, we're done. If we're using the Casio, normal CDF to the right of 0.83, we get 0.2033. Using the TI, oops, sorry, number 5. P was 0.5, X, that was 39, N was 71, and we got a right tail going on. And we get P is 0.2031 in this case. Regardless, that P value is greater than alpha. So we fail to reject the null. Where's our claim? The claim is in the alternative. There is not enough evidence to support the claim that among smokers who try to quit with nicotine patch therapy, the majority are smoking a year after the treatment. Year. So that would be our conclusion. Give me one moment. Yes, Audrey, look at the date. Hang on. Sorry about that. Okay. Next example. Testing Clarinex for adverse reaction. Clarinex is a drug used to treat asthma. In clinical tests of this drug, 1,655 patients were treated with a 5 milligram dose of Clarinex, and 2.1% of them experienced fatigue based on blah, blah, blah. Used a 0.01 significance level to test the claim that the percentage of Clarinex users experiencing fatigue is greater than 1.2% for those not using Clarinex. Does it appear that fatigue is an adverse reaction of Clarinex? Okay. So let's write down our hypothesis. Let's find it. Test the claim. There it is. that blah, 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 greater than 1.2%. So H naught, H1. Okay, so P is our parameter here, greater than 1.2%. Oh, that's going in the alternative. And let me write it as a decimal, 0.12. So N, let's go back and get all of our data, our statistics really. 1,655 patients, 5 milligram dose of Clearnex, who cares? And 2.1% of them experience fatigue. That's P hat. Again, write it as a decimal. Now if it's 0.01, and I believe that's that. Got P there, 0.012. So Q, 1 minus that would be 0.988. Use the calculator if you must. And that should be all we need. Let's grab our test statistic. P hat minus P over square root of P times Q. Now this time P is really small, so let's double check, make sure we can actually do this one. Oh, it's pretty big, so we should be able to. Really, every time we should be checking our conditions. But again, I'm not going to try and trick you on these. So remember that N times P and N times Q better be greater than 5. If I do that times 0.021, I get 35. So we're good to go. And on the other ones, our P hat was, it already told us 39, and that was 15% of 700, so I knew that was bigger than 5. But really, just check it every time. That's just to be safe. I might even ask you what are the conditions to be able to use the P test. Remember, it's a binomial approximation of the binomial using a normal distribution, so all those requirements must be met. Let's see. Oops, I need a fraction. Another square root with a fraction. So, wow, that's a big Z test statistic, 3.3626. So if we remember what our test statistic is, how many standard deviations away from the mean our value is. So looking at that, that's pretty far away. That's an unusual value. I'd probably say that, yeah, it's going to work, but that's why we perform a hypothesis test to be sure. So now, based on this test statistic, I'll look up the p-value, 3.36. Okay, what tail do we have? The right tail. 3.36 is right here. 3.36, yeah. So 0.9996. But that's not what P is. It's 1 minus that because we need a left tail. Sorry, we need to get the area to the left. We're given the area to the left. We need to get the area to the right of that test statistic. So 0.0004. There we go. TI users, shove it up in there. So P was 0.012. X, well, it's whatever this is. 2.1% of 1,655. Oh, got around that, 35. And was 1655. And we have a right tail. Okay. Okay, so this gives us a p-value of 0.0003 actually. And our test statistic was 3.417. That's a good bit of a difference there. And make sure I didn't mess up in anything. It could just be that big of a difference because we were working with such a small p-value. Make sure I didn't mess up Q in my head. I didn't. Okay. Well, that should be that. 0.021 minus 0.012. 2 times. Okay. So yeah, it's just that big of a difference. Either way, it's really small p-value, right? So it's not gonna change our results at the end. For the Casio, remember we're gonna take our test statistic and store it to A or B or C or whatever you want to do. And then we're going to do the null CDF greater the area to the right of our test statistic. And here we get 0.0004. Same thing we get here. Make sure you're able to read scientific notation. Pretty much just take whatever number this is, if it's negative, and subtract 1. So that's a 4. Take away 4, 1 from 4, we get 3. So that's how many zeros you're going to have behind your decimal before you get to this 3 right here. So now that we have our p-value, we can write a conclusion. P less than alpha. Oh wait, let me see what alpha is, 0.01. Yeah, it's still less than alpha. Reject the null. And when we talk about the null, we're talking about the null hypothesis. So the claim, oops, I didn't write down where the claim was. So the claim is greater than 1.2. That's in the alternative. If you forgot, claim is in the alternative. Reject the null. There's enough evidence to support the claim. Right here. There is enough evidence to support the claim that the percentage of Claire and X users experiencing fatigue is greater than the 1.2% rate for those not using Claire and X. Does it appear that fatigue is an adverse reaction to Claire and X? Well, that's what our hypothesis test told us. There's enough evidence to say that, yeah, it's called fatigue there. This is actually how they go about testing side effects, is using hypothesis testing. RL examples, people. That's what statistics is all about. We'll do a couple more. That's too many couples. Yeah, we'll skip this one. Let's go to these two. So I had to modify these two, and I'll tell you why in a minute. So if we read this one, a random sample of 300, I'll go ahead and write down my statistics first, and then I'll get my hypothesis test. 21 experienced nausea. So p-hat would be 21 out of 300. The new drug claims that at most 10% of patients who take this new drug for treating Alzheimer's will experience nausea. Test is claimed at the, that's not right claim. So that tells us our alpha is 0.05. So null, alternative, let's see what we got. At most 10%. So P is less than or equal to 0.10. That's the claim. Our alternative will be P is greater than 10%. And here's where I'm going to tell you why I had to make this problem, change this problem a little bit. You're not usually going to find the claim in the alternative unless you're trying to disprove it. Let's look at why. Sorry, I said claim in the alternative. You're not going to usually find the claim in the null. So there's only one way we can support our claim, right here. If the claim is in the alternative and we reject the null, then we support the claim. If we don't reject the null, then we can't support the claim. If the claim is in the null, there's not enough evidence to reject it, but that doesn't say we support it. There's not enough evidence to reject, there is enough evidence to reject it, there is not enough evidence to reject it. So we can't support these claims if they're in the null. What we can do is reject the claim. So if we're in real life, our claim is either going to be in the alternative if we're trying to support it, or our null if we're trying to disprove it. So most of the time, our claim is going to be in the alternative. So right here, we have the claim in the null, but really the drug manufacturer want to prove it. So actually, this problem originally stated that fewer than 10%, so that their claim would be in the alternative. We're going to work it this way, though, just to see what the difference is going to be. Okay, where were we? Now, P is 0.1, Q is 0.9. Find your test statistic. Again, this formula is on the top left of page 2 of your formula sheet, or the back of page 1 if you want to look at it that way. And I'm going to use the Casio so I can store it for later. Oops, I need a fraction. Okay. So our test statistic is negative 1.7321. Again, for p-value, we're only going to worry about the 2 places after the decimal. For the critical values, let's go ahead and use 4. So if you're doing the traditional method, go 4 decimal places. If you're using the p-value method, all you're going to have to worry about is 2 decimal places. So let's see, what kind of test are we dealing with? Again, it doesn't matter that our claim's in the null. we always look at the alternative for our p-value. Always. It's a right tail test. It's greater. Doesn't matter if the claim can be null. What matters is what our alternative says. So here we go. I forgot the number. Negative 1.73. Negative 1.70123. This should be it right here. Okay. 0.0418. 0.0418. But again, we're going to have to do 1 minus that so that we can look at the area to the right of that test statistic. P is 0.9582. That's a big p-value. So n was 300. X is 21. Oops. Put the 300 in the wrong spot. 0.1 for P. And it was a right tail test. So yeah, we get this huge freaking p-value. So yeah, we can definitely say that P is greater than alpha. We do it this way. Store that to A. Greater than, so A upper bound with infinity. And again, we get 0.9584 in this case. Regardless, that's a huge freaking p-value. We're going to fail to reject the null. Because P is greater than alpha. Since P is greater than alpha, we fail to reject the null. So our claim was in the null. We fail to reject the null. That means there is not enough evidence to reject the claim. Evidence to reject the claim that at most 10% of patients who take its new drug for treating Alzheimer's, how do you pronounce it properly, I don't know, disease, will experience nausea. So really this doesn't help out the company, does it? It's just saying, yeah, we can't say that that's false, but it doesn't say it's true. That's why whenever you're testing a product like that, you're going to want to put your claim in the alternative so that you can say, oh yeah, hey, it's true. It really is less than 10%. Okay. So again, there was this reasoning behind why our claim is usually going to be in the alternative if we're trying to support something. Usually we're trying to support something. I also had to change this one. A sample of 9,000 honeybees from one honeybee colony was tested for mites. A total of 228 of the 9,000 bees sampled were found to have mites. Test the claim that at least 2% of the bees have mites. Okay. So, our hypotheses. It's getting to be a long video. Okay, so at least 2%. That's greater than or equal to 2%. That's the claim. And then less than 2% would be the alternative. N was 9,000. P hat would be 228 out of the 9,000. Alpha is 0.01. P is 0.02. That makes Q 0.98. And that gives us the information we need for our test statistic. P hat minus P over square root P times Q over N. It's over 9,000. Josh would probably laugh there if you watch the video. So, get our test statistic. We have a fraction side of a fraction. Oops. Minus 0.02 square root of 0.02 times 0.98 over 9,000. And let's see what that gives us. 3.6. 140. So this time we're dealing with a left tail. Again, we don't care where the claim is for the tail. The tail is always from the alternative hypothesis. So P, let's see, well, the area to the left of 3.6 is going to be that. Is this positive? Yeah, it's positive. And I just remember that because look at the bottom here. 3.5 and up, area is 0.9999. And that is the area to the left of the test statistic. Again, I changed this problem. That's why these p-values are so ridiculously high, because originally it was the other. It was going to be a slushy, a right tail test. So, oh yeah, let's go ahead and show the TI people how it's done. P is 0.02, 228 over 9,000. It's a left tail. Let's see how many times this thing gives us. 0.9998. Okay. Test statistic 3.6140, same thing. Okay. Oh, and yes, I knew that 2% of 9,000 was bigger than 5, so we're good to go there. P-value, test statistic from the TI, Casio, got our test statistic, store it to our A or B or C or whoever, doesn't matter. Then we do a normal CDF. What are we doing? It's the area to the left of our test statistic, so negative infinity. A is our test statistic, 0.9998. So yeah, regardless, P is really freaking big, P is greater than alpha, we fail to reject the null. And if we fail to reject the null, and our claim is in the null, there is not enough evidence to reject the claim that at least 2% of the bees have mites. And the second part says, what would the conclusion have been if instead we tested the claim that fewer than 2% of the bees have mites? Okay, so fewer than 2%. So we'd still have a left tail test, and we'd fail to reject the null because we didn't change anything to P, we just changed where the claim was. So we'd still have P is greater than alpha, fail to reject the null. And if we did that, then we'd have to say there's not enough evidence to support the claim that fewer than 2%. That fewer than 2% of these have mites. So where your claim goes and whether or not we reject the null tells you how to write your conclusion. So again, usually our claim is going to be in the alternative, but not always. Pay close attention to where your claim's at. Let's see, I'll do one of these. Claim is 1%. Okay, so let's do this one. In a study of store checkouts, 1, 2, 3, 4 items were checked, and 20 of those 1,234 items were found to be overcharges. Okay. Based on this data, using a significance level of 0.05, test claim that with scanners, 1% of sales are overcharges. Claim that. Okay, so H0, H1. We want to test the claim that 1% of sales are overcharges. That's equality. P equals 1%. So our alternative would be it's not equal to. Our claim is in the null this time. So we can disprove this claim, but we can't prove it based on where the claim is. Let's see what happens. Calculate our test statistics. So we need P is 0.01. Q is 0.99. So our test statistic, 20 is P hat minus P over P times Q, or over the square root of P times Q over the N. So I'll go down to Casio. 20 over 1, 2, 3, 4 minus 0.01 over the square root of 0.01 times 0.99 over 1, 2, 3, 4. 2.19. So I'm going to store that. 2.1916. Again, 2.19 is what we're going to look up for our p-value. Okay, the two-tail. So p, we're going to actually need to draw this one. Well, actually, we don't need to draw it. We can tell that that's positive, so we could find the area to the right of it. But let's draw it anyway. So here's our mean. Here's our test statistic. It's to the right of the mean. That means we need to find the area to the right of the test statistic and double it. So let's grab the chart. 2.19. That's 0.9857. So 0.9857. Again, that's the area to the left of our critical value, our test statistic. So we need to do 1 minus that to find the area to the right of it. And then after we do that, we're going to have to double it because it's a two-tail. Thank you, Alternative, for telling us that. So 1 minus 0.9857 times 2, give me a decimal, 0.0286. So actually my p-value, I'm going to use the pi. Okay. 0.01 for p. X is 20. 1, 2, 3, 4 for n. Two-tail this time. And we get p is 0.0284. 0.0286, so very, very close. Test statistics, same thing. Okay. Casio, we already stored that test statistic to A. We found that it's to the right of our mean, so we're going to do that as a lower bound. Yeah, don't hit that times button. And keep it the same. That's not our alpha value, we have to double it. So I'm going to go to mode 1, answer times 2 is 0.0284. There you go. So if we're looking at alpha is 0.05, p is less than alpha. Okay. And this is kind of why I like the p-value method better if I'm using the TI. It tells you, okay, I'm sure the p-value is good for an alpha less than 0.05, but if it's a 0.01 alpha, if we want 99% confidence, ain't happening. 95% confidence we can do. Anyway, p is less than alpha, we reject the null. Okay, so we disproved our thing here. There is enough evidence to reject the claim that with scanners, 1% of sales are overcharges. Okay. So we have disproved this person's claim here. The only way that can happen is if the claim is in the null and we reject the null. That's exactly what we did here. So that's the p-value method. Make sure you pay attention to what your alternative is. Two-tail. You got to look at where exactly your test statistic lands. Let's look back at that chart. So if the test statistic is to the right of the mean, you find the area to the right and double it for two-tail. If it's the left, you find the area to the left and double it. Again, we only double it for two-tail. For right tail, find the area to the right, done. Left tail, find the area to the left, done. Okay, again, on your quiz tomorrow, or Friday, sorry, you will be required to be able to find the p-value and to actually be able to do the traditional method using critical values. Make sure you know both ways. Tomorrow we'll have our Zoom meeting for the first time, see how that goes. It'll be around 1:15. And that's it for today. And of course, it's